Kia ora, and welcome to Super Shading, optimizing home designs to avoid overheating risk. I think this is about our eighth webinar now, so we're just working through the key topics of what makes a super home. So just before we get into today's webinar, well, first of all, I'm Bob Burnett, Bob Burnett Architecture, and one of the founders of the Superhome Movement. This year, the Superhome Movement turns 10, which is a good milestone and unbelievable, really. I think time flies when you're having fun, and we've achieved quite a lot. And we're having a event, VIP event for our very important participants and partners. And so that's coming up soon. And then after that, we've got an event that's open to the public, which is a pop-up tour, but I'll talk a bit more about that later. So just today I'll welcome Metro Darren Valentine. Well, first of all, Andrew Krupa from Croftman Windows is going to talk about Windows, and Darren Valentine from Metro Glass will talk about solar control glass. And then we have Raoul from Archstone Consultancy talking about energy modeling and how that can be used to predict overheating and other things. Hopefully at the end we have some time for a panel discussion and some questions from everybody. So it's going to be a whirlwind presentation with all those. So as always, thanks to Jib as well, who is our principal partner, and also Brands and the other partners of the Superhome Movement. Without them, we couldn't do what we do, and also all the other participants and people that volunteer their time to make this what it is. So thanks to all those people. So yeah, probably not going to go into steal people's thunder. I'll let people talk about their own topics. And then my topic, I'm really just talking about the importance of design to avoid overheating. And pardon the pun, but it's a bit of a hot topic at the moment. We've seen quite a few media articles over sort of recent time. And yeah, the one on the right, 53 degrees inside your home. And you can probably see why with the amount of glazing on that facade, which is facing west. I know this house, it's in Christchurch, and we designed a townhouse next door, which had quite a different design with 900mm eaves and really optimized to prevent overheating. So when it's 20 something degrees outside, it shouldn't be 53 degrees inside your bedroom. So that's, if you Google a sauna without the fun, you'll be able to look at that article on YouTube. Or that's yeah, and then I think there's a lot of feedback from MB and the politicians about I mean, this one here I think it's quite funny, but it was about when Minister Pink was talking about insulation makes houses too hot, and we need to roll back the changes to H1 with the increased insulation standards, which beggars belief really is quite bonkers, and people in these sort of positions don't understand how buildings work. It's quite scary. But anyway, so what does bad look like? I think a big problem in terms of overheating is it's not too much insulation, it's faulty design and flawed design, and buildings like this, or even worse, ones with no overhang at all and fully glazed gables. Interestingly, these have a couple of chimneys, both of these. And yeah, so I'm thinking these are going to be way too hot, and also have far too much heat loss, and that's why they've got a fire in there. So chimney's a bit of a giveaway. Super homes don't have fires. If you're going to do that sort of design, you might as well grow your tomatoes or your avocados in there. because it's probably better for them that than as an environment for people. So there is a better way. So this house here, some people might remember it was on a Superhome tour. It's also been on Open Christchurch last year, and um, it's a really good example of a house that is just a constant temperature the whole time, and we've got some monitoring in there, and we can see that it is just fluctuates by about 1 or 2 degrees, plus or minus 1 or 2 degrees, with no cooling. And it's just got decent overhangs, and it's got a veranda that wraps around, and even careful attention with a little eyebrow here to, if your roof overhang, your eaves are too high, that's not going to work. So the shading needs to be at the right height. So brands have some useful information that's available. This bulletin here, I mean, most of it is good information. There's a couple of three things I don't agree with, but first and foremost, design needs to be site specific, and you need to consider the climate zones in New Zealand, and we've got quite a long country. So we go from quite a warm climate in the north to very cold in the south, and so the sun angles are different for the different latitude, longitude, and so Christchurch, where we're based, the optimum eaves we find often is about 750, and that'll be different in Auckland. It'll be slightly less. And if you use these, if you look at that bulletin, you can calculate based on the height of the eave and the height of the glazing and whether it's full height or not. You can calculate with a formula. You can calculate the size eave that you need, and that's probably one of the biggest kind of oversights. I think design isn't shading. Good shading is quite often absent, and sometimes houses don't have eaves at all. Works best for the north, and then round to the west or east, you're going to need probably more than eaves. You're going to need some vertical shading as well, in form of shutters or blinds. And Andrew from Kaufman Windows is going to show us his external blinds later, which is a product that we've just started using, which is really great. So yeah, I think that's fairly crude, but a better way, Rahul will talk to us about this, a better way is to energy model, and the better energy modeling packages will take into account the shading as well. Some of them do, some of them don't. So this house here, there's a 2 meter overhang on the roof, and there's also the deck is the same width. So the deck is shading the lower level. And incidentally, this is the house that will be on the pop-up tour on the 14th of June. So if you're in Christchurch, you'd be able to come and have a look at this. So you can see the extent of the overhang on the roof. This is one of the external blinds that I just mentioned. So it's sort of that, and that's the window over there. So it quite seamlessly integrates. And you've still got visibility through those, so you can still see the fantastic view through there. And then in this picture here, you can see there's louvers they're sort of retractable, they can open, and they can concertina back as well to allow light in when you need it and provide shading when you need it. And then down on this next level at the deck, there's a grate which is open, which is great to see to allow the light through to the next level. So the next level down can get a good access to daylight as well. So that's how that works. And the roof is sort of a tiered roof. So there's higher level glazing. There's a high ceiling in the main kitchen, dining, living area. So that image there sort of shows that. Yeah, so things like pergolas is quite useful, and you can grow plants, either grapes or hops maybe. There's sort of pros and cons in that. It's going to provide you shading mostly when you need it, but probably not entirely. And then you have to clean up the mess when the leaves come off. Same with deciduous trees. So this house here was designed as a passive house, and this tree here was included in the modelling for the design. And I'm just hoping that hasn't died, that tree. Otherwise, it'll be getting too hot. But yeah, and just the idea of cross ventilation, if you can have an airtight house, but it doesn't mean that you can't have cross ventilation and good natural ventilation as well. And so these are electrically openable windows um, at the top. Um, yeah, and this is a recent project which is probably the best we've ever done in terms of um, preventing, overheating or not having pretty much no overheating at all. So it's 0.01 potential for overheating. So I think a passive house is allowed 10% overheating, which would be 365 days in a year. That'd be 36 and a half days. This will have three to 4 hours that it could overheat, technically, in theory, but I don't think it'll overheat at all. And in this house, we've recessed the windows to the maximum so that they can be opened internally, so that the first floor windows can be cleaned from the inside, and the windows are configured with opening arrangements to allow that to happen as well. And then also there's a louvered area here for to have some shade for outdoor living as well. So just another example of a house where there's really oversized eaves. I think they're about 1.4 meters. And also the interfloor shading. So we've got at the mid-floor, we've got shading, and also down the side, we've got this little eyebrow as well. So that, quite often in a two-story house, the shading will be absent from the lower level. So there's a number of designs. We've taken this approach where we're shading both levels, and it works very well in practice. So yeah, just another view of that house. And then, this is a solid timber louvered shutter, so that slides. And then there's also the horizontal shading as well. So this has got horizontal and vertical shading. So when you've got this height of glazing, you really need that as well, because the roof overhang isn't going to be sufficient. So, and another idea is this wave shade, which if louvers are quite expensive, if you can't afford that, then you can do it with a fabric sunshade, and these ones are operable, so you can have them open or closed, which is quite good. And that's just another example of that. So yeah, this house actually has the external blinds as well. So, and then this house here has probably, I think they're 900mm eaves. Interestingly, Christchurch City Council say that if your eaves are over 600, you need to add that area to the site coverage, which is really counterproductive because 600 isn't enough in most cases. So we always push back on that, and we'll go for a resource consent and say, hey, we want the right amount of shading. We don't want our house to overheat. We don't want to be following these sort of counterintuitive rules from the city plan. So yeah, it's the same with the building code, seem to create these rules, and then you spend the rest of your working life trying to work around them. Ridiculous. But yeah, there are actually no requirements in the building code for overheating. The UK have a whole section on overheating in their building code, and I think Raoul might talk a little bit about that later, so I won't go into that too much. When you think about it, there's actually no requirement for heating in the building code, but the Healthy Homes Act have a requirement for living rooms to be 18 degrees, or I'd probably call it the Healthy Living Room Act, because the rest of the house there's no requirement. Anyway, we've got a long way to go, and Superhome, we're just into pointing out the really important things that you need to do and not waiting for the standards to change. At the end of the day, if you need a little bit of cooling, it's not the end of the world, because you might be, in most cases, particularly if you've got solar, the sun's shining when it's going to be too hot. So yeah, but the best houses we do don't need cooling, active cooling. So yeah, I think it's probably not much more for me to say. I'll hand over to Andrew now to talk about the windows. And then we've got plenty of time at the end for questions. And yeah, Andrew, do you want to take the wheel? I'll just get it onto the right screen for you.
Hello, Andrew Krupa from Kaufman Windows. So we started in 2017, seems a while ago now. We decided that we're going to import windows from Poland, which is Europe's biggest manufacturer of windows at the moment. And we have an option of both UPVC, aluminium, with Saint-Gobain glass. We pretty much standard now is triple glazing. We don't seem to be doing any double glazing. It's just the price difference, not justifiable. There's no savings in it. And German hardware. And why from overseas? Because there's so many options available, more options that like triple glazing and fully insulated aluminum windows are standard. And we bring everything assembled, so it's delivered in a container, ready for installation. And the windows, as Bob said, it's quite important part of the house design. And if you start with the design, you'll know how many windows you need, which side to avoid. So I won't go into that. And Windows seems to be the biggest heat loss, but it's also equally it's heat gain. So that comment that there's too much insulation, that's why the house is overheating, it's absolute rubbish. Why he's cooling his beer and holding in the foam. So that's just absolute completely wrong way of thinking. And the solar gain, it's a lot of comments we get from customers from North Ireland that, oh, we up here we don't need triple glazing, and it's not true, because that's how you avoid your solar gain. Insulation is the key. The more insulation you have, that's the better. And same with the windows. Triple glazing is just more insulation in the window. But it also gives you more, we'll talk about it later, and probably Darren will talk about, gives you more options of designing your glass specifically for what you want to achieve. And yeah, installation as well. So because if you look at the Windows, that's a standard sort of from lately H1 values. The R values of Windows vary a lot from standard Windows, which is like for Christchurch R.5 all the way to 0.9. And that is for New Zealand triple glazing. You achieve a lot better with better glass and better framing is up on 1.35. But even when it's brilliant, if you compare it to the walls are at least 3 times as better than Windows. So the Windows is the weakest point when it comes to the house insulation. So it's why quite critical to have the right windows. And you can do the same with aluminium. Doesn't mean the aluminium has to be worse than PVC. And installations is the thing. It's even if you have a good Windows, if you install it not recessed, you will lose that calculated R value. It's only calculated. If you do installation through thermal bridging, you might lose 30%, 25% of that R value. So you won't achieve even what you think you're buying. So installation is quite critical. And how you recess, how you tape it, you have to be quite diligent how you do it. And Proclima study of they have on the website, it's even small gap, like 1 millimeter gap, you will lose R value from 3.35 to 1.69. So it's a huge loss through just one small gap. So if you leave that gap around the windows, or the windows are leaking, not sealing properly, you will lose that R value. So that's more heat loss or heat gain. And so taping it up on both sides has to be quite critical. That's one of Dan's job. The boys are doing a good job taping up windows. And why European windows are better for ventilation, for overheating. The windows tilt in or open in. So you open window up the top, which is the hottest part, so it's much better for ventilation purposes. And having the windows opening inwards, apart from brilliant idea of actually using both tilt and turn function for micro ventilations. So you can, with those windows, install external blinds or rollers, shadings. If we are opening outwards, you won't be able to use it. So you can still crack the window open for ventilation and screen the sun shaded. So these can be motorized. I don't know, the video probably might should it work. Please go forward one. No. Anyway, they are motorized, so they can be connected to your house automation system. You can connect it to wind vane, or you can do it remotely via apps. So when you think it's too hot, you can drop them down. When it's too windy, they'll open themselves up just to protect it from the wind. And you can partly open it and stop it halfway, so you still have some daylight coming in. However, there's you have to be careful how you do it. As Darren will probably talk about the glass overheating, shading it partially, you create the risk of actually overheating part of the glass, and differential thermal expansion might cause it to crack. So we always use hardened glass for that, toughened glass. And there's other options as well. You can have Venetian blinds on the outside as well, exactly the same way, same company providing it. So there's lots of options with and with the glass, as I mentioned, Darren will probably talk about it. You can have triple glazing. We normally have low E facing both sides, so you stop the heat coming in through one face, and the other face stopping the heat coming out of your house. So it's a work both ways, summer and winter. So with triple glazing, you have that option of doing it and designing it different surfaces with low E. You can, like on the east side, if you want the heat gain, you can just stop, you just do one pane of low E glass in a different glass designs, different amount of heat you let in. So with the designing, you can actually specify actually what you need. But overall, if you have a better window, better insulated insulation, stop that heat, so more insulation, stop the moisture coming in or heat coming in through your house, through leaks. So use the heat recovery ventilation to control your comfort inside or your air inside, rather than letting your windows leaking through, relying on that. And talk to people, education, Superhome Movement, learn how to do things better. And it's just not just actually the other thing, as I was mentioned, I've been in Australia last week on short break, and I have seen cans exactly same as people do here, put aluminium foil on the inside of the windows just to stop the overheating apartments, which is completely crazy if you had to do that. The other thing is with the glass cracking or heat, if you do curtains or shades inside the house, that's already too late. The heat has already got through the glass. It's already inside your house. And what you may cause is actually overheating your windows or your glass damage, because you trap that heat with your concertina blinds or honeycomb blinds that are available lately. And yeah, don't accept anything less than triple glazing on a good windows and a good house design. So look for people actually to know what they're talking about, designers that are interested in your comfort and your comfort of living, rather than just selling you as the cheapest possible house. I think that'd be me.
Thank you very much, Andrew. That's great. Darren, if you just want to unmute yourself and share your screen. Darren Ballantyne from Metro Glass is next.
Can you hear me, Bob?
Yep, I think we're good.
Okay. That's encouraging. So hopefully this works.
I can see
Technology. Sorry?
I can hear you loud and clear, and I can see your screen.
You can see my screen. Can you see this? The slideshow?
Hang on,
Nope.
we might just need to stop sharing at our end first.
Stop being so sharing and caring. It's not like you, Bob.
Yeah. So.
Okay, hang on. I'll try again.
Yeah, just while we're getting that organised. Yes, I think, Andrew, it was really good that you talked about all the things that I forgot to talk about, which is great.
I probably forgot half of it, what I was going to say.
And, the idea of curtains inside, that's the sort of horse is bolted once the sun hits the glass, I think, unless you've got really good solar control glass, which Darren's going to talk to us about. But
Okay, can you see that?
yep, I think we're good now.
Awesome. Technology has cooperated with me. That's fantastic when that happens. First of all, I'd just like to thank you for the privilege of being able to speak to this group in this group setting today. And very briefly, I've been with Metro 11 years, and I have a keen interest in providing information on the benefits of high performance glass in buildings and work with stakeholders to ensure good selection choices are made, because certainly it's not a one-stop shop, but we do have options. We like to listen and then be able to provide advice. So what I've entitled this, as you see, is Super Shading with a View. But what I'd like to first of all start off with is just an interesting, when people are looking at budgets, is a kitchen bench top upgrade can easily involve an extra cost of $8,000 to $10,000, and a upgrade to high quality ceramic tile with a bespoke frameless shower, which can be in excess of 10,000, and then you can double it if you also do the main bathroom. So just if people would like to remember that when I get to the end of the presentation, it will have more relevance why I've put that in there. So in terms of why windows are important in homes, I'm not going to read through these all line by line. In fact, what I'd like to share with the group is that I actually have put one of our high-end solar control glasses in my own home. Unfortunately, mine's not the one with the that great, fantastic view. Mine's the one with those two lounging dogs in there. And what you're seeing there, because one of the misnomers that's out there is that when you go and put a solar control glass into a home, and this Sun-X Grey has an SF of 24%, so around 24% of the radiated heat is coming through. But I could pay people to lie on the ground and pretend like they're enjoying the warmth, or you can actually look at what naturally occurs. As we know, cats and dogs will find the warmest spots, and those photos were taken at about 10 o'clock last Saturday, and both of them, and I know myself, is that you can feel the warmth. So again, just putting to bed some of the misnomers, although again, happy to talk through later, because at the moment I've got 10 minutes to show you a few things about this type of glass. Now, the first thing I'd like to do, because I know there's a lot of contradictory views out there, and to be fair, my job is to listen, find out what people are after, and then provide solutions using the offerings that we've got. So solar control glass on its own, I acknowledge, and so does Metro Glass, it's not the silver bullet solution. It's about being able to offer people the opportunity, if they have got big views and perhaps there's challenges with being able to put certain other types of methods into control overheating, then we do have a range of options. And that is the point too, is that depending on what's being wanted and calculated and modeled, we're happy to help with being able to make some bespoke and specific reports, and basically assist the job get the outcome. And the example you see there, that's a beautiful house there, and with a combination of design factors there, I believe the inhabitants of that house are very happy, and that's got one of our lesser solar control glasses in there. It's a product called Extreme, and you know it worked perfectly for what was being modelled for that house. So in terms of the actual solar control glass itself, I mean, it's not witchcraft. It has been around for decades, but certainly the tech and options available have increased. And again, it's about offering designers and people building homes the option to have a more or have a more passive type of solar control versus actively having to arrange things, or as I say, when there's other design challenges. In terms of how the solar control works, I thought I'd throw in this diagram here that shows that it factors in terms of SHGC, or solar heat gain coefficient, which is also known as SF, solar factor. They're both actually exactly the same thing. And it shows with 100% sunlight outside, in this particular instance, for this type of glass, what the energy is, and also what the radiated heat is, which then gives you that SHGC figure. And what I also threw in there, because it's interesting to me, again, when there's a lot of discussion about the number of times a house is at risk of getting exposed to overheating. And it's very hard to, and again, that might come through in the next presentation from Raoul, in terms of some of that discussion, because ultimately you can't just take the outside temperature, because as Bob showed earlier, which was a more dramatic variance, what's happening outside greatly increases inside if there's poor design and poor building components in a home. So what have we got? And we've actually got other options outside. So this is our typical residential offering. And I've actually been a bit playful here and thrown the product along. So if you cast your eye along the top, there's XL, Extreme, Sun X Grey, Sun X Reflect. Then in the triple glazing, we have some double low E triple glazing there, which is a Thermalite, Solar Pro, and Solar Pro Plus. And again, we'll help out anyone that comes and talks to us in terms of how we can best help with a project. But when you look down, and I've put the orange box around the column that is in terms of this discussion is the important one, which is the solar factor percentage. And you can see a great variance. We've thrown in the clear on clear double glazing, and there's also a clear on clear triple glazing, just so you've got a baseline as to how effective these lowies can be in terms of reducing solar heat gain. But what I was also going to point out is that you can also increase passive heat gain if that's a design element wanted in the house. And so the XL can be turned around. It's typically put on, and I've got a diagram first at the bottom there that shows the surfaces of a double glazed unit. And surface 1 is the exterior face. Then you've got 2, 3, 4, with 4 being the inside of the home. And so, for example, if someone was wanting to get passive heat gain, because sometimes that is actually being targeted, it might be for certain rooms in the house, which was something that was touched on earlier on. But if they want to increase the heat, you actually swap it around from that surface 2, where low E is typically put in most New Zealand homes, onto surface 3, and you get a significant gain in the amount of heat coming in. So because of the layering of the glass, again, we can help projects get the targets that they're after. So then I come down to, if you remembered that second slide in, what the costs of the bench top and the cost of the shower was. And then there's been a lot of discussion, especially up north in drinking environments with builders, where cost is put as a primary reason as to why people wouldn't want to look at investing in upscaling or upgrading the performance of their home. And so what I did is I went away and I grabbed 20 just random orders from our system of homes that were ranging anywhere from 150 square meters up to 220 square meters of home. And they were pretty typical houses. And what I did then is I converted what had been priced, which was the H1 compliant low E standard glass that gets used in a lot of homes, in fact nearly in most homes, and converted it into our Sun X Grey, which is one of our premium solar control glasses. I then went and factored in a margin for the fabricator, so the person that does the frames, because they buy the glass off us, and they quite rightly, put a margin on so that they can carry on doing business. Then I also did put a margin on for the builder, and again, I won't divulge them because I'll upset people, but I did go and ask a couple of people, what typical margins would look like. And I believe everything that I'm about to say is very realistic. So using that, the cost increase for a solar control glass is anywhere in the $3,500 to $4,000 mark. So again, thinking back to what a bench top costs or what a shower costs, I think that with the performance you get, then that is a good investment if that's what you're targeting. So I see my 10 minutes is up, so I will stop there, but we'll hang around for any questions that might come in later. Plus also, if you do want to note down my number or my email address, I can share it, then feel free to reach out and contact me. I'm here to help. Thank you. Now I'll try again handing this back to you, Bob.
Thank you very much, Darren. That's great. So now we're going to hear from Raoul about energy modelling.
All right, good afternoon, everyone. Thanks for joining. I'm going to give a presentation about how we can use energy modeling to ensure energy efficient and comfortable building design. My name is Raoul Markford. I'm a sustainability engineer and director of Artstone Consultancy. I specialize in energy modeling and also in environmental rating tools such as Greenstar. I'm originally from the Netherlands, been there now for 5 years and worked on a variety of projects. So we're going to talk about 3 things today. First, some general knowledge about designing for the sun, then moving into energy modeling, and lastly, we're going to touch upon overheating and quickly look at a case study. So to start off with, the power of the sun is truly astronomical. Well, look at the image and the size difference. And in 1 hour, the sun gives the Earth as much energy as we use in the whole year combined. So if there's one key takeaway I would like you to have for today, is that the power of the sun is huge, and we need to take that carefully into consideration when designing buildings. So how do we allow for the sun in building design? And it's actually quite complex because it depends on a variety of factors. We've seen in previous presentations today that sun obviously enters through windows, and windows are simultaneously the largest source of heat gains for a building, but also a very large source of heat loss. So that's one complexity, but another complexity is that we have different heating requirements throughout the year, but mainly that there are various factors that influence how much heat from the sun we get into a building. Some of those factors we have in control, and those are related to the window design, orientation, specifications, and how we use it. But there's also a number of factors that are out of our control. And those are mostly related to the intensity of the sun, different throughout the day and the year, the location, and very challenging, the weather. So if we want to design for the sun, we need to take all those factors into consideration, and that's where energy modeling comes in. Quickly on the New Zealand Building Code, I think most people listening today will be aware of this, but unfortunately, the current building code does not ensure comfortable and energy efficient buildings. Well, I started off the presentation with saying how important the sun is, but the building code ignores the impact of the sun, and there are also a few oversimplifications and issues mentioned here. So the building code doesn't ensure for comfortable and energy efficient building design, but how can we ensure that? And this is where we move into the second part of the presentation around energy modeling. To start off with, what is energy modeling? Energy modeling is using software to simulate and predict the energy consumption, but also comfort levels of buildings. And put very simply, it's like a virtual test drive for a building. There are a number of different energy modeling tools out there, and what I use is called climate-based software. And that means it uses hourly weather data to run simulations, and that makes it very suitable for solar studies, shading studies, and overheating analysis. And this is where this software separates itself from other packages, such as the passive house package, which is mostly focused on keeping a building warm, but not necessarily on avoiding overheating. Energy modeling is not just about calculating energy figures and comfort, but there are a whole bunch of things you can do, which you can see here. Examples are daylight studies or carbon studies and envelope improvement studies. So questions energy modeling can answer. I'm not going to go through all of them, but as an example, what are the optimal shading dimensions to reduce overheating? Or what is the most cost-effective way to increase energy efficiency? Yes, all important questions that energy modeling can help with. What does this look like in practice? What's the workflow of energy modeling? So it starts off with engagement, which is preferably early on in the design. I then use the concept architectural plans and put those in the software and assign relevant components such as insulation values. I run a simulation and then analyze the data. And the output of that are two different kinds of reports. The first one is an energy report, and that includes an energy breakdown. And what it means is pretty much it shows how much energy the building will use, where the energy comes from, and how much energy you need for heating and cooling. And the second part of this report is an envelope improvement study. And this is a very interesting simulation, which consists out of hundreds or even 1,000 different options of the thermal envelope to find which option works best for the project, both in terms of cost as well as performance. The second report is related to overheating analysis for indoor comfort, and also daylight and visual comfort study is included in that. Next in the workflow, there will be a meeting to discuss these results and potentially to remodel a design improvement, and I also provide an H1 report. For the purpose of this presentation, you can see energy modeling offers a lot of different outcomes, but I'm just going to look at overheating analysis for today. And that brings us to the last part of the presentation, which is a case study on overheating. So this case study is for a single-story residential house located in Geraldine. And you can see in the red marked area the main room, which is the combined kitchen, dining, and living room facing north. And I'm just going to focus on this room for today. So an overheating assessment, what does it consist of? I look at three different aspects. First, how often and how severe will the living room overheat? Second, what causes this overheating? And third, probably most interesting, what are different options we can do to reduce overheating? So how often and how severe does the living room overheat? Well, there are various ways of doing this, but I think the best practice method is following a standard from the UK. Bob mentioned this already, and that's called TM59. And that was specifically developed because in London overheating is a big issue. Important to note with this standard is that it only looks at natural ventilation, so no mechanical cooling, and it uses a climate file that represents a warmer than typical summer. So what that means is that there would be 6 summers in a row that are, let's say, regular weather, and then a 7th really hot summer. And that really hot summer, that has been taken into consideration in this analysis. And that's important because it's sort of a worst case scenario, but it also becomes, we can expect more of those summers with climate change. So this standard looks at 3 different aspects to indicate overheating. And first is the number of hours where the temperature is too hot. I'm just gonna jump right into the results. And there is a threshold or 3% where the temperatures can be too hot. But you can see for this project that threshold is exceeded, so there will be overheating. The second factor it looks at is the number of days where there is back-to-back overheating hours. And for this project, you can see that there are 17 days where overheating can be classified as severe. And third, the standard looks at extreme overheating hours. So not where it's just too hot, but where it's like extremely too hot. And there are 36 of those hours in this project. So we can conclude that during this warmer than typical summer, this living room is at a high risk of overheating. All right, so we know the living room is at high risk of overheating. What causes this overheating? Well, the indoor temperature is the result from various different heat transfer processes. And in the report, I go into more detail on this. But for today, just kept it simple. And in the graph, you can see the operative temperature, so the temperature, how we perceive it, on a hot summer day. And you can see that it exceeds 35 degrees. Where does this heat come from? In the bar chart in red, you can see the heat gains, and in blue, the heat losses. And in the light red, you can clearly see that heat is mainly coming from the sunlight. So overheating is caused by solar heat. So now that we know it overheats and that's caused by the sun, last part of this presentation, what can we do to reduce overheating? So you can separate these strategies into passive design strategies and active design strategies. And passive design strategies we're going to look at today is, can we increase natural ventilation to cool the building down? Can we reduce the amount of glazing? Can we add shading devices? And last, what glazing type suits this project best? So for today, I'm not going to talk about mechanical cooling. So first option to reduce overheating, can we increase natural ventilation to cool the building? Just as a general note, the energy modeling software I use is really good in modeling natural ventilation, and that is based on wind data. And also in general, natural ventilation is only effective if the outdoor temperature is lower than the indoor temperature. Well, it makes sense because otherwise, if you open the windows, you actually heat the building up. And this means that we can test the effectiveness of natural ventilation. And here too, I'm gonna jump right to the results. So for this project, the natural ventilation is already effective. So we can conclude from that increasing the natural ventilation is not gonna help cool the building down. Second option to reduce overheating is, can we reduce the amount of glazing? Well, you can see this project actually is not using that much glazing already, 21% window to raw ratio. So that is a good percentage. However, you can see that the living area that's on the right of the elevation has a disproportionate high amount of glazing from the door sliders. But the clients didn't want to compromise on that. They found it the main design feature they wanted to keep. But what they did do in other rooms in this project is removing or reducing the skylight area, which specifically in the bedroom significantly reduced overheating. Second to last, and probably most interesting, is, can we add shading devices? We saw overheating is caused by the sun, so with shading devices, we can block that. And what's great is that energy modeling allows you to define the optimal shading dimensions. So this is not rules of thumb, but you can exactly calculate from different shading types, such as you can see in the image, what the best dimensions are for any specific project. And all these different options can be tested in one large simulation, which makes it quite effective. And to finish the presentation today, what is the best glazing for this project? So we've seen in the previous presentation that glazing is engineered with a low E coating that lets a specific amount of heat through. So this typically ranges from 25% to 75%. So there's a trade-off between heating and cooling energy. If we choose a high percentage and let a lot of solar heat in, we obviously need less energy for heating, but we need more energy for cooling, and also the other way around. So we need to find an optimum. So for this project, what is the best low E coating or solar heat gain coefficient for energy efficiency? In this bar chart, you can see on the y-axis the percentage of solar heat coming in, ranging from 25 to 75%. In red, you can see the amount of energy we need for heating throughout the year. And in blue, the amount of energy we need for cooling throughout the year. And this graph really nicely shows that trade-off. So if you look at the total length of red and blue, you can see with a solar heat gain coefficient of 25%, we need most energy, so we are worst off. Whereas from about 60% onwards, the total is more or less even. We also see here that if we let more heat in, we need more energy for cooling than for heating. So my recommendation for this project was to use 60% solar heat gain coefficient, taking into consideration climate change. All right, to wrap up, what we've seen today is that the sun has a massive impact on building design, and this is determined by a range of factors. The New Zealand Building Code doesn't allow for these factors and unfortunately is oversimplified. Energy modeling is the best practice method to overcome these simplifications and to ensure a building is energy efficient and comfortable. And the value of energy modeling is not just in identifying the issues, but also in highlighting which solution for a specific design works best. So we really quickly discussed energy modeling today and touched upon overheating, but there's a lot more that can be done. So look forward to talk about that further in a later session.
Oh, that was really great. Thank you very much. So we've still got about just under 10 minutes. So we'll just click in to see if there's any questions. But in the meantime, I do these webinars and then I remember the things I forgot to talk about. But, probably a key point is we're living in a warming climate. And by 2040, the number of days above 25 degrees is predicted to rise by 40%. So that'll mean that our homes need to be designed better in future, obviously. And the amount of months that we have hot weather will be increased. I think in the past decade, there's 7 out of 10 warmest years on record being recorded. And yeah, so that's the challenge. And I think today we've seen some really interesting ideas and potential solutions to overcome that challenge, which is only going to get greater. So thanks to all the presenters. It's been a great session. And yeah, so any questions? Matthew, sorry, I missed it. Can Darren explain the difference between G value and SHGC, solar heat gain coefficient? I think it might be the same thing, but I'll let Darren answer that one.
You're right, Bob. It's the same thing.
Yeah.
Yeah. So the only other one that is out there that can cause some confusion is shading coefficient, and it's a different formula. And what we're trying to avoid is we very much focus on solar heat gain coefficient, otherwise known as solar factor, and as otherwise designated as G value.
Cool. Thanks for that, Darren. Yeah, I think, a lot of what we've talked about today and what we've heard from our esteemed panel of presenters is quite technical. And to my way of thinking is this sort of seems to be this tendency to jump to the specifications when probably the starting point, or definitely I think the starting point is just the size and orientation of the windows to start with, and how are the windows, what are the windows and how are they incorporated in the building in terms of the orientation to north. But also, in terms of the use of the rooms, you don't want your just thinking about the layout and the flow and the orientation. You don't necessarily want your kitchen on the west side with too much glazing if you're going to be cooking dinner at night, creating heat in that space anyway. So those sort of fundamentals really are the starting point. And then once you've got that right, how you deal with some of the challenges like a beautiful view that you need to capture become where we can take advantage of some of the technical solutions.
Probably just what's the reason for the windows? It's quite often latest designs are always down to the floor, and in a bedroom you probably don't need the windows or the doors down to the floor. It's just a window.
Totally.
And it's really hard to shade it.
Yeah. I really like the external blinds and the fact that you can actually still see through them, but they can give you some control over the solar gain and keep the solar gain out. And conversely, if you pull curtains, you can't see the view anymore. And in Christchurch and further south, there's this idea of thick curtains are going to make the house warmer, but you have a window for a reason. You have a window because you want light and you want a view. And if you're going to keep the curtains drawn all the time, then that's a bit grim and you're missing out. So now, are there any other questions? Does a different G value make the glass look slightly different from the outside or reduce the visible light on the inside? Darren?
The answer is it depends on the low E type that's being used. So yes, when you start looking at that, and in that presentation, although I didn't focus on it, there was a thing called visible light transmission, VLT. Got a variety of names, but that's part of the selection process. And for example, the house that was in that photo that was beautifully designed, I think by you, Bob, wasn't it? So the light transmission for that house is actually it's got a 40% solar factor in it, so quite a high performing solar factor there, and the visible light is 74%. Now, to give you an example, a piece of clear on clear glass, or a double glazed unit is 81%. So you will get so you can play with the solar control, still get good light, just as some people are actually looking for less light, less glare. And so, again, you can play around with the Sun X. It has a visible light transmission of 41, which gives which gives people the sense of privacy and cuts down on glare. In terms of reflectance, yes, if you go for another type of light, we've got one called Sun X Reflect, and that is, again, used for privacy purposes primarily. So rather than it being the G value, it's actually the other aspects of the glass that are designed into those low E coatings.
Yeah, cool. Thanks.
That's the fun bit.
Yeah. So we're almost at time. If anybody's got any ideas for future webinars, just yell out, because we've got a lot of ideas, but it's probably most important is what people want to hear about. We're thinking about a specific webinar on energy modeling. And I think that would be quite a valuable one. So under the events section of the Superhome website, there's past webinars if you want to look back at videos of different topics. And also there's information about the upcoming events like the pop-up tour that's coming up at the house in Balmoral Lane. So thanks everybody for joining today. And we're just on 1 o'clock, so I think we'll leave it at that unless there's other questions. I can't see any other questions. So as always, just drop us an email if you've got any other questions anyway. Thank you.